Welcome to today. Thank you very much for joining us for Future Flight Fridays. And today we get to talk about a very exciting topic. My name's Simon Buckley. I look after low emission mobility at the KTN. We get to talk about zero emission infrastructure. Now, there's been a lot of talk. You saw the PM's 10-point plan, where we're looking at getting to net zero, and that's across all industries. And one of those is aircraft. There's a lot of R&D and technical work being undertaken within zero emission aircraft. And for that, and big part of the puzzle, we are going to need the infrastructure to support that aircraft. So we've got a really exciting lineup of speakers for you today. The important thing from today and the aim of what we're trying to do with Future Flight is we're exchanging knowledge, which will allow you to gain new insights and can maintain those connections around the future flight space so that we get to net zero quicker. And it'll also help you, the listener, find technology or services you might not have known existed, or to connect to people that you might not have connected to otherwise. So the next slide, please. So we've got, as I said, 3 exciting speakers across the zero emission infrastructure piece. Now, this is electrical infrastructure, this is hydrogen infrastructure, and they're the 2 main areas we're concentrating on today. So the way the session will work, we're going to have 3 10-minute presentations, and then you'll have a chance to ask some questions, and I'll ask them to our panelists, who I thank very much for joining me today. So kicking us off first is Mehmet Emre. He is a technology and innovation consultant at UK Power Network Services. He has over 7 years experience in transport and energy industry, and specializes in ultra low emission vehicles and the associated infrastructure. And he's got a wide range of expertise, from feasibility studies to implementation. So Mehmet, if I can ask you to go for your slides, please.
Thank you for the introduction, Simon. Welcome all, good afternoon. I am Mehmet Emre, Technology and Innovation Consultant from UK Power Network Services. And today I will be presenting some of the ideas and concepts around the projects we want to build for electrical infrastructure for electric and hybrid aircrafts of the future. Next slide, please. So just want to say a quick few things about ourselves. We are UK Power Network Services, the commercial arm of the DNO, UK Power Networks. The work we do ranges from consulting to design and build, capital financing, and once we build and installed, we will operate and maintain the electrical infrastructure. I work in the consulting team, which spearheads the innovation within the company, and our aim is to provide full end-to-end life cycle. Next slide, please. These are the industries we work on. I just want to concentrate on 2 main ones and join it to Future of Flight. So we work in aviation. We provide electrical infrastructure and maintain and operate electrical infrastructure of Heathrow, Stansted, and London City Airport, and more. We also work on logistics and fleets. So we electrify fleets for UPS, Stagecoach, and other fleet operators, which brings us to this presentation where we joined our expertise in aviation, electrical infrastructure, and electrification of fleets and aircraft to understand how we can electrify future aircrafts and what are the challenges are. Next slide, please. So what is the main challenges in electrifying the flight? The main one is that aviation in its current form is not sustainable. If it doesn't change the way it is going, it's forecasted that it will be the largest greenhouse emitter within the transport. But interestingly, not just transport, if we achieve 2050 targets and not decarbonize our aviation, it could result in 46% of our CO2 emissions in 2050. So that's almost half of all our emissions coming from aviation. The main challenges are twofold. First one is the aircraft itself. So due to low battery density, high battery prices, it is very expensive, and it's not technically feasible to develop an aircraft that can that can be electrified at the moment, which results in lack of interest in developing these aircrafts in the first place. And the second part of the challenge is, even if we have the electrical infrastructure, electrical aircrafts or hybrid aircrafts, how do we charge them? Because they will need significant amounts of power, and there's lack of infrastructure available at the moment at the airport, but also at the grid side as well. Next slide, please. So the way we want to approach this is that, according to IATA, the electric taxis will come in early part of this decade, so 1 or 2 seater electric air taxis, which will move on to hybrid electric aircrafts in the second half of this decade, where we can have hybrid electric aircrafts of 15 to 20 seaters. And from 2035 to 45, we are looking into developing electric or fuel cell aircrafts for 80 seaters. So we can't electrify or decarbonize regional, national, or short journeys, but when it comes to continental and intercontinental flights, we need significant breakthroughs in battery technology. Thus, the main challenge is to be addressed for aviation and aircraft developers, but the main challenge for us is, how do we charge these aircrafts that require megawatts of power? So to understand that, we developed few needs and requirements to help us develop a solution. One of which is that we want to charge the aircraft during its layover. So when it comes to the apron, it stops there for 20 minutes, half hour, 40 minutes, whatever that duration is, to take the passengers off and clean and put passengers back on for the next flight. We should be able to charge the aircraft rapidly at that point, so it's ready to go for the next destination. The second requirement is that we need to install new infrastructure or upgrade the existing one. We need significant amount of infrastructure. We're talking about megawatt, at least a megawatt charge points per aircraft. If you think about Heathrow, that the total demand at Heathrow is around 60 megawatts. So that means 60 aircrafts is matching up, charging at the same time, the same as what the demand is at Heathrow at the moment. So it means that we need a whole electrical infrastructure at the airport just to charge the aircrafts. We also need to do smart charging, so we don't want to just connect and charge and put all the impacts on the grid and have very high demand. It's very expensive to work that way. So using clever smart charging would help us to reduce some costs. And we don't see electrification as just electrifying the aircraft. We see it as a whole ecosystem. So we want to include other distributed energy resources, such as public EV charging, staff charging, charging the aircraft on the air side, and electric vehicles on the air side as well, and also integrating renewable generation and battery storage into the aircraft ecosystem as well. And most importantly, all these solutions needs to be economically viable. So it encourages airports and aircraft manufacturers to develop these solutions. Next slide, please. So there are several solutions that we identified. I'm just going to mention 3 for now, 3 potential ideas that can solve this challenge of charging the aircraft. There could be more. We are currently investigating what would be the best option to go forward with this. So one of it is plug-in charging. So basically, the aircraft arrives to apron. High-powered charge points are plugged in, and it charges while it's turning over. Second one is mobile charger. So this is more like a truck with a battery stored on the back of it. So battery charges at the depot. It goes to the aircraft and charges the aircraft. The aircraft battery. And the third one is battery swap. So we swap the battery of the aircraft and replace it with a new one. I will go into details on the next slides. Next slide, please. So plug-in charging, grid connection is connected to terminal load, which is what aircraft needs, but also we will connect to ultra-rapid chargers to charge during the day and overnight chargers to charge overnight. This requires whole electrical infrastructure to be installed and built at the airport. I also put a orange box into smart systems. This is an optional system, but it's a necessary system to integrate. Smart charging will control terminal load, all the charge points and other assets such as generation storage and public EV charging. And it will optimize the total electricity network, minimizing the cost for the operators or the airports. but you can connect directly to the grid connection as well, which is the simple way of doing it, but in the long term it will be very cost inefficient. So the advantage of this solution is that it's something that we can do, just install the infrastructure, plug into the aircraft and charge. But the disadvantages would be that we need to charge the aircraft within the half hour, and it may not be possible to charge to 100%, fully charge the aircraft using plug-in charging. And it will also require significant infrastructure works at the airport airside as well. Next slide, please. Next solution is the mobile charger. Briefly mentioned this earlier. So the mobile charger would be a truck that has a massive battery at the back of it. So it will charge at the mobile charging station. When the aircraft arrives, the truck and the batteries will go to the aircraft, connect to the aircraft and charge the batteries. So using a battery to charge the aircraft's battery, basically. The advantage of that is that you won't need all electrical infrastructure on the airside. You can just simply have a depot of charging infrastructure and a mobile vehicles to charge the aircraft. The disadvantage is, again, as mentioned, you need to do rapid charging within a short amount of time. You may not be able to do it fully. If you do it fully, with the current battery technology, it could deteriorate the battery lifetime very quickly, charging at very high powers very frequently as well. So your life cycle of the battery will reduce significantly. And there's also overnight option here as well. So when the aircrafts don't fly, they can charge overnight at a slower rate than the rapid charging. And the final solution, the next slide, please, is the battery swap. So this technology is that you will remove the batteries from the aircraft and transport it to a battery swap and charging station. Charge the batteries there. When they're full, you can put that battery onto the next aircraft. So it doesn't require two sets of batteries. You can simply use the existing aircraft batteries and just cycle them over with the different aircrafts. And it also ensures that you always have a full state of charge battery, so you don't need to do high rapid charging. You can control the charging, and when the vehicles arrive, you simply swap it very quickly during the layover time. The main disadvantage of that is battery swap technology is not fully developed. There were a few battery swap technologies that has been tried in EV sector. One of them haven't been very successful. The other one is still under development, so it's very early stages of development at the moment. What's important here is that we need to develop a whole infrastructure of battery charging stations, logistics of how we will transport these batteries across, and also some processes and equipment and installation processes to remove the battery from the aircraft and install it again. Hello?
Yeah, hi, Mehmet. We can hear you.
Hi.
Do you want to?
Sorry, I got cut off for very quickly. I think it's fixed now. Can we go to next slide, please? Yeah, so those were the three options. They all have their own advantages and disadvantages. We're going to do a study on them to understand which option is the feasible option, which one works best, not just technically, but economically as well. And what we want to achieve at the end of it is that optimized costs for not just the airport operator, but also the aircraft operator as well. Realize a lot of savings around how we will use the energy, earn revenues from these batteries and aircraft infrastructure, provide services to the grid, and also maximize the efficiency of the electrical infrastructure. We don't want to just install the infrastructure to maximum demand. We just want to understand what is the best way of going through it and installing this infrastructure is. By developing this infrastructure, we are hoping we can accelerate the electrification of aircrafts, because we are solving one of the challenges that is a barrier to it. And we also want to improve the business case for electrification through using electrical infrastructure to earn revenues, improve the savings, and finally, and importantly as well, to reduce the aircraft emissions and improve the air quality as well in and around the airport. Next slide, please. So what's the future? So first, an initial task for us is to understand what is the best way of installing and developing an electrical infrastructure for future hybrid and electrical aircrafts are. So we will try to develop a system or using a smart charging system we adopted from EV charging to maximize the efficiency and minimize the cost and also potentially earn some revenues as well. But the way we charge the aircraft, we want to do a technical assessment of each solution. So far we identified 3 main solutions. We are still trying to identify more. And based on the feasible solutions, we want to understand the economic feasibility of each solution. And once we've done the technical feasibility study and economic analysis, we want to determine the best or technical mix. And moving forward, we would like to install and demonstrate this infrastructure at an airport setting to have a practical understanding and collect data to improve the system. Looking at the long term, the way we see it is that there is a potential to electrify regional and local national aviation, and also change the way the aviation works as well. So instead of working on hub to spoke model, we can have more independent flight destinations as well, where local airports are being used more frequently due to very low cost airplanes and aircrafts. Yeah, it's very exciting stuff, and this decade will be very interesting to see how it will progress. That's it from me. Thank you. If you have any questions, I'm happy to take them.
Perfect. Thank you very much, Mehmet, for that. And so we'll do a Q&A at the end. So please ask any questions and put them in the YouTube chat, and Hannah will send them across to me, and we'll answer them later in the session. So one of the things I mentioned there was battery swap and being able to charge the plane up quickly enough. Our next speaker may be able to help with that. So her name is Beth Dawson, who's Major Project Manager at Fuel Cell Systems Ltd. Beth has been within hydrogen and fuel cell industry for more than 16 years. She became the Major Project Manager at FCSL in July 2016, and her focus is now on the deployment of hydrogen fueling and fuel systems. She was Innovate UK Women in Innovation Award finalist and an APEA award finalist, and she's also been very closely involved in some future flight activities that I'm sure she'll go into. So Beth, if you can come to the stage, please.
Absolutely. Okay, so I believe I've got control of the slides on this one. So I've got a lot of them because it turns out I can gas about hydrogen all day. So I'll rattle through them, and we'll try and give you a quick background on that. Okay, so quick bit about us, Fuel Cell Systems Limited. We are not a fuel cell manufacturer. We are an installer and integrator. Just in case you're not in the know, a fuel cell is a little bit like a battery in that it produces electrical power, and it does it in an electrochemical way. So you're using catalysts to generate electrons. So a bit like a battery, but instead of a battery that can run out of charge, it's a battery that doesn't run out of charge as long as you keep the fuel coming to it. And that fuel can be hydrogen or something that is hydrogen rich, like a methanol or a propane, something like that. And it's our job to match up customer power demands with available fuel cells from the marketplace. The two that are shown on the screen here, the little black box is a box of power that's been used by the BBC for wildlife filming for Winter Watch and Spring Watch. The snowy one is a mountain range, it's a radio repeater station on top of a mountain range in Antarctica. Both quite niche. Our main area of deployment is CCTV towers, as they are able to stay on their own for sort of 6-8 weeks at a time without any interference. Okay, so my slides seem to be moving forward without any help from me, which is curious, but let's not dwell. So my main message today is that electricity and hydrogen are symbiotic. So people seem to think that it's an either or, and I'm here to say it's not. It's both. Obviously, we want to step away from fossil fuels and start making the most of our renewables. The way to do that is to incorporate some sort of storage, because renewable power is by its very nature intermittent. The sun doesn't always shine, the wind doesn't always blow. So we need to be able to store the excess when it's available, and then deploy that again when the renewables aren't there. And one of the ways to do this, and I totally agree that batteries and supercaps are going to form part of this, but another way of looking at this is to do with hydrogen, and how hydrogen can act as that sort of buffer and storage mechanism. You can generate hydrogen by running an electrical current from your renewable power sources through water, H2O, and split it into hydrogen and oxygen. You can then trap that hydrogen and store it ready to use it again when you need additional energy. You can actually burn hydrogen, and that is carbon free. It's not completely emission free, but it's carbon free. But also you can run it through a fuel cell then to generate electrical power. And what's true on the macro level is also true on the micro level. So from a system manufacturer point of view, when you're looking at powertrains, it's just electrical energy. So there's quite a lot of components that are in common between battery electric vehicles or drivetrains and fuel cell powertrains as well. It turns out electric motors don't care where they get their electrons from, whether you pull them from the wall or whether you generate them on board using a fuel cell. So the propulsion technology types we're looking at here are sort of battery, and then moving up the chain in terms of how much power is required for your application, be that to do with extra weight or additional range or both. As you move up that scale, batteries start to top out after a while, and it's not to do down batteries. They absolutely have a place. It's a jigsaw approach rather than one magic silver bullet. So when you're operating just one vehicle, obviously a battery could make sense. When you're operating fleets of vehicles, or when you're operating emergency service vehicles, or anything that needs 24/7 operation, hydrogen starts to win out, just because of that fast refuel time and the extra range. Typically you're seeing 300 to 400 miles from a passenger car using hydrogen. And then as you start getting heavier as well, buses, HGVs, even into trains, hydrogen can start making sense. Just going to go back one, there we go. And out into planes and shipping, obviously very large vehicles, and I think that's moving out into future as well as we move out there. I think there's still a question mark about the approach that can be taken for both of those. They're both very highly polluting industries, so it's about picking and choosing the one that's best at that point. And I think, you know, we've got a little while to think about that, but we've got all those stages beforehand. Okay, so hydrogen transport today then, it is here already. So that's showing the three most popular passenger vehicles. That's the Mirai, the Nexo, and the Clarity. Also scooters, forklifts. You can get a double-decker bus that's hydrogen powered rather than battery. Also HGVs and trains. They are here already, and that's really good to see. Also, hydrogen planes are coming through as well. So this one is it's called the High Flyer project. It's an Innovate UK funded program. This is company Zero Avia, who have retrofitted a Piper Malibu plane, initially with a battery drive powertrain, and they flew it on that. And then they've been swapping out that battery with the fuel cell version now as well, and they have flown it on pure hydrogen, and so that's very gratifying to see. This is currently a 6-seater little sort of island hopper plane, but the plan being that they will have sort of 50 to 100 seat planes coming through. Going to future, Airbus announced in September that they were hoping to have hydrogen planes by 2035. They are looking at liquid hydrogen rather than gaseous hydrogen, but they're quite excited about the potential for having zero emission powertrains for their aircraft. And they've got a few designs, obviously, that they're looking to take forward, and we shall see. It's very exciting, but it's gratifying that a large player can see that. Now, for hydrogen to be usable as a fuel, it really needs to be available at the right time, place, volume, pressure, and purity. And anyone who works in the hydrogen space will tell you that absolutely everything we do is all about safety first. People do fret about hydrogen much more than they need to. But as a fuel cell integrator, what we find is that the issue is never the fuel cell. The issue is always the fuel. And this is something that we found that the car manufacturers have hit upon this as an issue first, and indeed those trying to look at doing buses, just because the vehicles are there, they all work brilliantly. The issue is where we're going to put the fueling, how much and what cost, and how's it going to be built for future. So the purity then, fuel cells are quite picky. They're like 5/9 hydrogen, very pure hydrogen, and part of the method for getting to very pure hydrogen will depend on your production route. So typically the majority of hydrogen in the world is currently made by steam methane reforming, which is the process on the left there. So methane is a fossil fuel. Obviously it'd be better to step away from that. So producing hydrogen via electrolysis, it's much cleaner inherently. All you need to do is give it a little bit of drying afterwards and it's good to go. So talking about volume then, now I'm going to use volume completely unscientifically here. I'm talking about how much hydrogen do you need? I know, but if I start talking about kilograms or molecules, it starts getting a bit confusing to those who are unscientific. So what I mean is, it feels to me fairly inherent that a train is going to need more hydrogen than a bus, which will need more hydrogen than a car. And then when we're looking at ships and planes, we're talking about a step out again. So what this means is the tank size on board will vary according to the demand placed by the weight and range of the vehicle. And then the fueling structure that sits behind that will also need to be matched up to the volume, or to service those transport needs. So is the vehicle coming back to base? Stop moving forward. Is the vehicle coming back to base? How many vehicles do you have? What size is the tank? And is it better, therefore, to bring hydrogen into site, or is it better to generate on site using your own electrolyzer? And it's a bit of a Rubik's Cube of a problem, and what is appropriate initially, which might be bringing it into site, might not work for future case scenarios where it might be better to produce on site yourself, at which point you will need electricity to do that, be that on site renewables or be that via grid, which is why it's not an either or, it's both. To talk about pressure then. So gaseous hydrogen needs to be pressured really to be useful. Obviously the same amount of molecules in a smaller space is going to mean a higher pressure gas. And typically what we're seeing at the moment is that the transport applications are either using 350 bar tanks or 700 bar tanks. That's about 10,000 psi. You can see the difference in the tanks there. Obviously the higher pressure tank is a lot thicker, so it needs more processing, more material. All the components for the higher pressure systems are just more expensive at this point in time. And they are being serviced by the stations that are popping up across the UK currently. There's about 12 at the moment, and there's more coming. And they are starting to be integrated into forecourts, which is very pleasing to see. But 12 isn't enough. Even with the range of sort of 300-400 miles per full fill on a passenger car, it's not enough at this point in time. Which is why we've come up with a range of products to sort of service that initial hydrogen need. So everything is possible, from a very, very small amount of hydrogen right up to the full static stations, whatever's most appropriate. So this is the littlest one. This is my mini hydrogen dispenser. It's a hydrogen jerry can. We've integrated that onto an AA support vehicle, which got used during the Nexo launch. It did run out and we did have to stop in a lay-by and give it a quick puff to get it onto the next place. Next up is the high van. We haven't built this yet, but we've got a lot of inquiries for it. This would be a mobile solution to give an almost full fill, depending on the requirement. Similar to that, so sort of a static high van would be the high cube, which we have integrated for the HydroFLEX train refuelling. So this is the UK's first hydrogen train, and it can take hydrogen from any source, be that MCPs, which is what the gas you can see in the centre picture there, the red, and that's what they are, or an electrolyser, or indeed a tube trailer, and will dispense at the right pressure for the train. We've also got a truck, which we used very successfully for the Metropolitan Police scooter trial. 15 months of 7 vehicles, and we had over 500 filling events, and it all worked beautifully. That was at the 700 bar pressure. And we also refueled the Toyota Mirai using the truck as well for one of their PR events. So this is the exciting bit for us that we've been doing recently. So we built a second truck. This was for the High Flyer project, the Piper plane that I mentioned earlier. So this is matching up the hydrogen infrastructure with the hydrogen need at this point in time. So the hydrogen truck is appropriate for this plane for this demo. Obviously, there is a thought that in future that will need to be beefed up. But they've currently got an on-site electrolyser to keep the truck topped up, and then we're filling the plane on a flight-by-flight basis, and it's working beautifully. But the point being, all of these are sort of modular and scalable. So as the hydrogen demand increases, so you can sort of build up the supply side behind it. So yeah, that's me. Feel free to ask me questions. Thank you very much indeed.
So thank you very much for that, Beth. I'm sure there'll be plenty of questions for you in the Q&A. And about how you can help support the shift towards hydrogen aeroplanes. So our next speaker, and apologies if I mispronounce this, Michael, is Michael D'Onofrio, who is a founding member of GridServe, which is a British sustainable energy business that develops and builds, owns and operates mission-critical clean power applications. Now, this includes a range of charging hubs, and utility scale hybrid solar. But one of the things you might have seen in the press recently was that Michael led a successful consortium, including technology, academic and public sector partners, to build the UK's first electric forecourt located in Braintree, Essex in 2019. So Michael, do you want to take it away and tell us a little bit more about how you see that fitting within the aerospace world?
Thanks, Simon, much appreciated. Don't worry, people have pronounced it much worse, so that's not bad, and you've already stolen my introduction. But yeah, so here today, I'm founding member of the GridServe team and currently a member of the advisory board. And what I wanted to talk about, I'm not going to use any slides actually, but sort of wanted to go last ahead of the Q&A session, really talking about what we can learn from the electrification of ground transport and how we can apply that to the air. Because ultimately, we need to solve this problem, sort of land, air and sea, to be able to really sort of decarbonize our world. So as Simon said, GridServe is pursuing what's called a sun-to-wheel model. So taking electrons from the sun, typically from a utility scale sort of solar facility in the UK, of which GridServe has built 2 at York and Hull, and then taking those electrons through either direct connections or kind of virtual connections through the electricity grid into the wheels of cars as sort of the first step. Why cars? Why didn't we sort of pursue boats or planes? The main reason is because the battery technology and the commercialization sort of cars, especially as it relates to electric vehicles, has tended to go first. And what we're now seeing is, passenger cars, everyone can, probably heard at least of Tesla and sort of the adventure that they have gone on sort of commercializing electric vehicles. And now that the rest of the industry is following, it really creates an opportunity to sort of start to build a system around it, which I think, Matt talked about, that, you really need sort of electrification of the infrastructure as the electric vehicles come on at the same time. Otherwise, it doesn't work. If we take the Tesla example, they built both a charging network and electric vehicles and kind of sold that together. And it's probably one of the reasons why that is now, one of the most valuable car makers in the world, is because they really thought about the system problem that needed to be solved as we move from fossil fuels into, in this case, electric vehicles. So as Simon indicated, GridServe, along with our consortium partners and backed by Innovate UK, OLEV and Hitachi Capital, building a next generation electric forecourt in Braintree, Essex, which, touch wood with kind of national lockdown, will hopefully launch in Q4 2020. And that's really a demonstrator project to demonstrate that you can integrate, solar, battery, and ultra rapid electric vehicle charging. So we're talking about, 350 kilowatt charging that can charge your vehicle in sort of 10 to 20 minutes, depending on sort of the size of the battery of your vehicle. There are dozens of chargers. And while that time is while you're on the site, there's retail facilities, there's place for the kids. There's a way to sort of spend that time effectively. And it was really designed with that kind of passenger electric vehicle in mind, because you can see sort of in public data that, new car sales are starting to increase. You're starting to see sort of mid-single digit sort of percentages of new car sales in electric vehicles, and even through sort of 2020 that has continued to increase. It's been one of the few areas of car sales that has remained constant and increased as a mix of the electric vehicle fleet. And really, so if you have that passenger vehicle, that's the essence of an electric forecourt, right? But that doesn't mean that an electric forecourt can't be used for other applications, right? Because, just like a petrol forecourt is used to both do cars, bikes, HGV vehicles, if it's appropriate. You probably can't charge a plane on a petrol forecourt because it doesn't quite work. But if you start applying that to an electric forecourt and you just replace all the petrol infrastructure with electric infrastructure, it actually creates some quite interesting possibilities as it relates to aviation. And one of the things that hasn't come up sort of so far on this webinar is drones as an example. So think of that as micro-mobility for the air. So one thing you could use an electric forecourt for, because you've got a 5 plus or minus kind of megawatt grid connection. You've got a space, you've got half an acre, 1 acre, sort of 2 acres to work with. You've got the roof of a retail building, and potentially you can use that as a drone hub for the local community, especially if you build, 100 electric forecourts across the United Kingdom. And if you had it as a drone hub, then as an example, I'm just sort of throwing it out there because this is really sort of about sort of UK research and innovation. You could then have, trucks, electric trucks, distributing from distributors to the electric forecourts. You could take all those parcels, you could put them on the top of the electric forecourt, and then you could use drones to deliver that to the local community. And you could do that with, minutes, hours sort of delivery times, rather than using our road networks, which are becoming increasingly sort of congested and are very expensive to both build and maintain. So that's just one example that I wanted to bring up today of, how you could apply the lessons learned of land-based electric vehicles to air-based electric vehicles. That's a micro example as well. And it would be very easy to charge the drones overnight, or you could simply swap the batteries if you really wanted to, and use some of the lessons from other areas of micromobility, of which, Europe is really leading the world in some of these, as it relates to scooters, mopeds, bikes. For those of us who had, very brief opportunities to travel to Europe this year, it's quite interesting to see just how many of those scooters, that are doing swappable batteries, for example, or how many electric mopeds are there. And it appears, based on sort of UK government regulations, that, that's going to start coming to the UK if it hasn't already. And that sort of technology, we can keep using that technology and apply it to aviation is, I guess, one of the key messages that I wanted to leave today. Whether it's a scooter, whether it's a car, whether it's a truck, if you just kind of match that up to what you need to do in aviation, then that's quite interesting. And there's lots of lessons to learn there. I think we also talked about fuel cells. Fuel cells have been around for a really long time, right? One of the challenges with fuel cells, though, is, the fuel works. And, if you use, I'm going to use green hydrogen or some form of green fuel to be able to do it, that's great. The fuel cell itself is absolutely great. I guess the big challenge there is just the billions or trillions of infrastructure that needs to be built, which is currently being built for electrical infrastructure for passenger vehicles, to sort of do that for fuel cells. So, maybe fuel cells are better for the heavy industrial applications, which I think was indicated, or it's better for those remote sort of cell towers where you're replacing, a diesel generator with a fuel cell, because it does not have a connection to the grid. And that could be a really kind of, awesome way of solving it, even with a bit of hybridization with the battery. So there's really, there's different parts of the vehicle ecosystem that we need to consider. There's different types of technologies. So, fuel technologies, if I use that term. So aviation, electricity, hydrogen, fuel cells, they're all different types of fuel technologies. And then there's different pieces of infrastructure. And I think, especially sort of the private sector, whether you're an entrepreneur, an investor, an executive in the UK and globally, it's really the job of the private sector to see the right market opportunity at the right time and then execute accordingly to be able to build businesses, which is primarily my background. So for context there, I did my MBA at Harvard and was co-president of the Energy and Environment Club. So it's been a passion of my life for the last sort of 20 or so years, sort of the intersection of sustainability and technology. But really, it's the job of the private sector to line it up. And alongside that, find the right private-public sector partnerships, for example, like we've done with the demonstrator project in Braintree, Essex, which, is materially sort of funded by both private and public sector capital to show to both, Great Britain and the rest of the world that it can be done. Because once you see it in the real world, it makes it much easier, right? You can send photos, you can take videos. When national lockdown is over, in the right tiers, we can go visit the electric forecourt, and whether you have an electric vehicle or not. And then, you can start to really think about, hey, if this existed in the world, what could I do next, right? What's the hardware? What's the services? What's the software? What's the data and analytics? You can start to really build around this as we really sort of, move to a low carbon and ideally a zero carbon economy over time. So apology I didn't have slides, but I really, it was quite fascinating to listen to my two previous panelists and then be able to build on them with that core theme of, what can we learn from other types of transport and how can we bring that to aerial flight or aviation, if we want to use that term. So Simon, with that, pass back over to you and looking forward to a bit of Q&A.
Thank you very much, Michael. I think that was really interesting for me. I found that the really interesting point there was about the drones and about how that could be part of an integrated transport solution. I think in the UK, we need to have an integrated cross-modal platform, multimodal platform to go towards net zero. And I think that's a good example of how that might happen. So thanks for your questions. Please keep them coming in. We got to 1 o'clock. So we're going to try and get through all the questions that you answer. Obviously, if there are too many questions and we don't get to your question, we'll try and give you a follow-up, but please don't take offense. So the first question, I think we asked to two people. I'll ask Mehmet first. What is the impact on grid peak and local communities with multiple rapid charging points at airfields / EV toll nodes? So Mehmet, if you want to take that.
Yeah, sure. So as mentioned, the charge points to charge the hybrid or electric aircraft needs to be very high powered. We're talking about megawatts. So this requires a significant upgrade, not just in the airport to update electrical infrastructure, but it also requires distribution network to upgrade their infrastructure as well. That's why we think the smart charging option with other resources such as renewable generation and battery would be very useful to reduce that demand on the actual electricity network and optimize the demand from the airport. In terms of how local authorities will operate, the way it will work is that once you apply for a grid connection, the network operator will upgrade the grid at a cost, depending on how much power you will need. So there will be installation on upgrade of the existing network. What using the smart charging and whole energy ecosystem, the benefits of that would be that the local area would have generation on battery storage, which they can benefit from in near future if they opt for like a local energy system type solution.
Okay, thank you very much. And maybe, Michael, you can build on that and see whether your solution that you've got might actually be able to assist with some of those local energy issues.
Yeah, Simon, actually, that goes really to why the founder of GridServe called it GridServe, actually, if I kind of start with that. So GridServe is both serving electricity from the grid into cars, but it's also using that electric forecourt infrastructure to stabilize the grid. So one of the things we're trying to do, now it may not be possible in every city application, especially in an inner city, because the real estate and the grid connection doesn't work, but trying to include batteries on each electric forecourt. Because what that allows you to do is that allows you to use the grid to charge the battery, and then the battery to be able to charge the cars. So from the grid's perspective, it's not as impactful as just putting a ultra rapid charger and sort of destabilizing the local grid. However, that was one of the things we're testing in the Innovate UK project to see how much we can optimize it. Is it economic, et cetera, et cetera. But huge amount of learning so far on how to do that to make it a sustainable solution for the entire country.
Yeah, thank you. And what type of battery are you looking at installing in these forecourts? How large? How many kilowatt hours?
So, lithium ion batteries, because we're dealing with primarily short duration problems. If you were dealing with a longer duration problem, you would potentially use other technology. But as the sun comes up every day, you have to deal with it for 24 hours at most. And then batteries that are in the megawatts. So, if you kind of roughly add it up, if you have a dozen cars sort of charging at 300 kilowatts, which is, very unlikely in the short term, but you need to build infrastructure for the next sort of 10 or 20 years, you can quickly determine that you're going to have a multi-megawatt load on your site, and then trying to cover as much of it as you can with the battery. And at some point during peak times, you may have to use the grid as well. But trying to find the right kind of balance there is really one of the main objectives of our demonstrator project.
Perfect. Thank you very much. So next, we'll switch to hydrogen. So Beth, if you could take this one, please. What is the electrolysis efficiency to produce hydrogen that you achieved? And this might obviously be different across different projects.
It is, yes, very much so, and very, very different depending on the type of electrolyzer that you use as well, and the size of it. So it's a bit how long's a piece of string, unfortunately. But I think the key thing to say is that the fewer steps you make to change energy from one state to another, the more efficient your system is, full stop, on a whole system basis. So if you get to use renewable power directly, do that. If you can store it in a battery and use it well that way, do that. Yes, changing energy state from using electricity to split water, store the hydrogen, and then put it back through a fuel cell, you are losing efficiencies the whole way through that system. Agreed. I totally agree that there's no getting away from it, and that's it is what it is. I do think people get hung up on efficiencies in a way that they don't in other areas. I don't think anybody gets in their petrol or diesel car and thinks, well, I'm driving this and it's only 30% efficient. You just don't. So I don't quite understand why people get a little bit hung up on, beating fuel cells about the head with it, really. But the good thing is that it enables us to make the most of our renewables. And as I wrote on the Q&A bit just a few minutes ago, we currently lose the last figures I saw were 1.8 terawatts of electricity from stranded wind assets alone in the UK. So that is purely offshore wind, and purely when it's too windy for the grid to accept all of that electrical power, you end up with a wind turbine that's stationary during a windy day. And it's because that system doesn't, it's not perfect, it's overproducing. And I would say that we are literally wasting that amount of energy. That's enough energy to power the entire Transport for London for network. it's so much energy, and we're not using it, and it's a damn shame. And I just think if we use that energy instead to split water, generate hydrogen, store the hydrogen, and then feed that back into the system as and when you need it, we lose nothing. You know, yes, that requires a spend up front, but we will be making the most of our current renewable assets today, and I think that's worth doing.
Yeah, and I think Beth, just one brief point building on that is, you know, I always love asking entrepreneurs or investors or technologists, you know, what's the round trip efficiency at both an electrical and a heat level? And you just see people's minds explode trying to explain that to you. And then you also need to say, what's the use case you're trying to address? So what's the use case? Then tell me the round trip efficiency. Then I'll tell you whether it's good or not. And like just that very simple discussion, you can quickly tell whether someone knows what they're talking about or not. Yeah,
very true.
Thank you very much for that. And we'll stick with hydrogen. So there's another one. So it says, great to hear about the hydrogen infrastructure, but this is asking about regulatory issues in aviation. Yeah. So what timeline will there be for airports to adopt hydrogen on a kerosene apron?
Okay, so we're currently refueling at Cranfield Airport. So Cranfield, obviously, it's a small airport. There's no getting away from that. And they have a variety of experimental planes that are tested there, and so they are a bit more open to the thought of having slightly weirdo different fuel types around. But the key things to make hydrogen safe, and like I said in my presentation, people don't fret about hydrogen, and actually it isn't 100% necessary. One of the best things about hydrogen is that every single molecule of it is trying to go that way at 45 miles an hour, and not an awful lot can stop it. So the biggest thing you can do in a safety case is have clear air above you, let it go. You know, it's not even a greenhouse gas. It's so small and traveling so fast that it escapes the Earth's atmosphere. So, you know, there's a lot to be said for that. It's not like a liquid fuel that drops and runs and sets fire to everything else as it goes. London Fire Brigade love hydrogen as a fuel because, you know, they say to us, well, by the time we get there, it's all gone, hasn't it? And we're like, yep. But the key things about integration into an existing airport structure are separation distances between different fuel types. I mean, that is true of existing fuels as well. So if an airport is using both kerosene and also diesel fuels, they will be kept well apart from each other. So it's a different fuel again, so keeping the hydrogen well separated from the other fuels. And then having a clear emergency response for each of those fuel types should, you know, the worst case scenario happen. And we've integrated that successfully at Cranfield with using both of those principles. But greater than that, I would say, within the confines of that of the High Flyer project, we have also been putting together the safety case documentation in order to roll that out to the other airports. So we're looking at 3 other airports within the High Flyer project. Again, they'll be fairly small airports at this point in time because that's an easier sell, and because it will be mobile equipment, we can, you know, drive it to site and keep it well away from everywhere else, which I think is you know, it's an easy integration at this point in time. But it's using the same principles, and we also have the CAA and others involved in that safety case planning as well. So it's coming.
Great, it's good to hear you've got the CAA on board to kind of help with this, because obviously they're central. So next we will go. Maybe this is quite a quick one, I think, because it's not quite about infrastructure. It's also more about the actual power for the airplane. So do we, pardon my ignorance, have validated / recognised certification for flight batteries and fuel cells? So Mehmet, maybe if you could take at least the battery element.
Yeah, sure. I think being in the aviation industry, it is heavily regulated. You might be aware that several years ago there was an issue with one of the Boeing aircrafts having battery issues, which we need to be taken off the flights until that battery issue has been resolved. So I am assuming the same regulations and standards for existing batteries on the aircraft will apply to traction batteries on the aircraft as well. And the challenges, if you're flying couple of thousand feet in the air, you're in minus temperatures. Lithium batteries doesn't like minus temperatures or heat or too cold. So there needs to be a whole set of innovation and technology to make sure that these batteries are kept safe and regulated at the same time, and without compromising its performance.
Great. Thank you very much.
Yeah, thank you.
Sorry, we'll try and go, because we've got still a number of questions left to go through on the Q&A. So if we can try and be nice and
sorry.
on the answers.
I'm a talker. Sorry.
Very quickly, Beth.
Yeah, very quickly. Same certification as it would be for any other aircraft component, really. And one of the good things about fuel cells is that one of their exhausts is heat, so you can sort of help to keep it all at a pleasant temperature for operation anyway, which is good. But yeah, they are stringent rules. We are meeting them. I'm not concerned about it. It's a process that needs to be done.
Perfect. Thanks very much. So Michael, one for you. It's a bit more of a general on this. How will e-fuels come to affect or compete with electrification? Would it not be better to race for making cheap enough green synthetic fuels?
Great question. I think an e-fuel is referring to a liquid fuel. Let's call it a green liquid fuel. I think the difference there, I would say, is the nature of what you're doing. So one is related to electrons that kind of go through cables at some point, and one is a liquid fuel. So you really need to think about what is the use case you're trying to solve, and how do you go back and do it. Our thesis at GridServe is the cheapest source of power is the sun. So, and the easiest way currently, other than kind of, relying on nature itself, the current way is with a solar, with a PV panel, the technology is quite mature. You can turn sun into electricity extremely cheaply. You can build a tens of megawatt utility scale solar project in York in the United Kingdom, which is not the sunniest place on earth. You can hybridize it with a battery, and it is economic to do so. If it's economic to do so in York, it's economic to do so, okay, maybe in the far reaches of Scotland, someone will find somewhere where it's not economic to do so. But that is a pretty mature technology. So you need to strike the right balance between speed and impact, which is what electrification offers now, to help us hit the SDGs, the European Green Deal. We've got 2030 targets we're trying to hit. And then you need to start kind of making those venture bets or those innovation bets for 2040 and 2050 now, so you can potentially have the other solutions that you get there. I think it would be a loss for society, for business, for generally people, if we did not capitalize on the technologies that we have now to make a huge impact. And if we find some better technologies over the next decade, let's start investing with them and kind of get there. But the climate, if anyone's watched David Attenborough's latest film, the problem is now. The problem was 20 years ago. We can't just sit around and wait. Otherwise, our children will be suffering from the problems of us as adults. We did not take the action now.
So I think, so thanks very much for that. And I think actually we didn't quite manage to get all your questions answered. So apologies for that, but we are out of time. I think it's a good point to leave on that we need to act now, and we need to change the way we do things for the future of our planet. It comes down as simply as that. So thanks very much to all our speakers again. So to Michael, to Beth, and to Mehmet, and thanks to all the staff behind the scenes. So in the new year, we're going to have no more of these future flight sessions in December, but in the new year we'll have a whole new batch. So please keep an eye out for those, and I believe they will continue with the same type of format. So short, sharp, little knowledge gathering into interaction sessions. So once again, thanks very much for your time. Please get in touch with us, particularly if you want us to answer one of those questions that we didn't get to answer, or you want to hear more about future flight. And obviously there's a website there you can also go and visit for a little bit more information. So thank you very much for your time, and have a good afternoon and weekend.